Hello, this is Dr. Hanaa Assil, and this is Unit 2, June 2022. So, the first question says, which equation represents the standard enthalpy change of formation for aluminium oxide? First of all, let's remind ourselves, what is the meaning of standard enthalpy change of formation? It is the enthalpy change that takes place when 1 mole of a compound in its standard state is formed from its constituent elements in their standard states under standard conditions. Okay, so what do we have? Aluminium oxide. Okay, the standard state of aluminium oxide is what? It's a solid. So in that case, all of them are correct. But the enthalpy change of formation is the enthalpy change that takes place when 1 mole of a compound. So as you can see, C and D are wrong because they're forming 2 moles. So that's not right. And then we want to form it from its constituent elements in their standard state. Of course, the standard state of oxygen is a gas and it is diatomic, so it has to be O2. So the only possible answer here is, or the correct answer here is A. How does an oxidizing agent change during a redox reaction? Let's take a look at a redox reaction. This is a redox reaction where iron plus copper 2 plus gives copper plus iron 2 plus. And you can see that the iron is oxidized, so the iron is the reducing agent. The copper 2 plus is reduced, the copper 2 plus is the oxidizing agent. So the oxidizing agent is the substance that does what? That gains electrons, or it's the substance that was reduced. So gains electrons, that means my answer is A or B. Now, when it gains electrons, for example, in the equation we have copper 2 plus, when it gained electrons, the oxidation number does what? The oxidation number decreases. Remember that oxidation number is basically the charge on the species. So Cu2 plus has an oxidation number of +2. Cu with nothing on it, oxidation number is 0, and that means the copper 2 plus changed from +2 to 0, so the oxidation number decreases. So my answer here is A. Which of these compounds would be expected to have the highest boiling temperature? First of all, let us look at these compounds. So this is A, and that is a tertiary OA alcohol with how many carbons? 4 carbons. So this is 4 carbons with OH. This is 4 carbons also with OH, but this is a straight chain. Now, C is a branched chain with 1, 2, 3, 4, 5 carbons, and D also has 5 carbons, but it is a straight chain. Now, what is the rule? Which one has highest boiling temperature? We said, first of all, the longer the chain, the higher the boiling point. So if I'm looking at the first alcohols, which are A and B, you can see that both of them have the same number of carbons. So the one that has more carbons should have higher boiling point. But then we also have other rules. So we can say a branched chain will have lower boiling point than a straight chain, and we need to look for hydrogen bonding. If any of these does hydrogen bonding, then it would have higher boiling point. That's something that cannot do hydrogen bonding. So if I'm looking at which of these should have higher boiling points, it is the one that has OH, because an alcohol can do hydrogen bonding, and hydrogen bonding is stronger intermolecular forces compared to the normal van der Waals or London dispersion forces. So that means that my answer is A or B. Now, which one would have higher boiling point? We said branch chain has lower. So that means A would have lower than B. So B has the highest boiling temperatures among all of this. Okay, what is the name of this compound? Well, they are all potassium chlorates, but the difference is the oxidation number. How do we calculate oxidation number of chlorine in each of these? Now, in the formula he's asking, you know that potassium is group 1. Group 1 always has oxidation number +1. Oxygen, each oxygen has oxidation number -2, and that means I have 2 of them, so that is -4. Now, the total should be 0, and that means chlorine would have -3, and that means this is potassium chlorate 3. Question 5 says a small piece of calcium is added to a beaker of distilled water. Remember, putting calcium into distilled water, we said calcium will sink, and this is cold water, so it will form calcium hydroxide. So first of all, you should know that when we put calcium in cold water, it should form calcium hydroxide. So my answer is C or D, but remember, how do we write the formula of calcium hydroxide? Calcium is in group 2, so valency 2. So we have to put a 2 under the hydroxide, which has a valency of 1. And then we balance. So you can see that the balanced equation for this reaction is D. Are we okay? Okay. Which element is oxidized and which is reduced when calcium reacts with water? Okay, this is the reaction when calcium reacts with water. We said it gives calcium hydroxide plus hydrogen. So, which element is oxidized and which element is reduced? You can see that calcium changes from calcium metal to calcium 2 plus. This is increase in oxidation number. This is oxidation. So the substance that is oxidized is calcium. Now, hydrogen in water changes from H2O to H2. That is loss of oxygen. That is reduction. So the element that is reduced is hydrogen. Which is the ionic equation for the reaction of solid barium carbonate with dilute hydrochloric acid? How do we write ionic equation? Well, you write the equation normally. Barium carbonate is a solid plus hydrochloric acid to give what? It will give, this is carbonate with acid, so it will give salt plus carbon dioxide plus water. Write the state symbols of each of them. Remember that we ionize only anything that is aqueous. So barium carbonate is a solid, it remains as it is. So we don't have C or D. C or D is wrong. HCl is aqueous. Of course, after balancing, you have 2H plus and 2Cl minus. The barium chloride is aqueous. That's barium 2 plus and 2 of the chloride ions. Carbon dioxide is a gas. Water is a liquid. You do not ionize solid, liquid, or gas. Now you cancel whatever is the same on both sides of the arrow, and that means I am left with this equation, which is the same as that in A. Are we okay? Okay. The presence of ammonium ions in a compound can be shown by adding a reagent, warming the mixture, and testing the gas evolve. What was the test for ammonium ions? What is the reagent? Ammonium ions react with a base. So the reagent was add aqueous sodium hydroxide. So my answer is C or D. And we said if I'm testing for ammonium, we add aqueous sodium hydroxide. On warming, we get bubbles of ammonia gas that turn what? Damp red litmus to blue. Remember, ammonia gas is alkaline, so it will change red litmus to blue. Then he says aqueous chlorine is added to an aqueous solution of potassium iodide. a non-polar organic solvent is added. Now, when chlorine reacts with potassium iodide, of course, chlorine is more reactive than iodine, so it will displace it, so you'll be left with iodine in the mixture. Now, if we add an organic solvent, what is the color of iodine in an organic solvent? You should remember that iodine in an organic solvent is violet, or purple, if you want to say that. Okay, a titration is carried out by adding dilute sulfuric acid from a burette to aqueous sodium hydroxide in a conical flask. The indicator is methyl orange. Do you remember the colors of methyl orange? You should know the colors of methyl orange. It's yellow in a base, orange when neutral, and red in acid. So what did he have in the flask? He had sodium hydroxide in the flask. So when he added methyl orange, he started with a base. So you're starting with yellow. And then when we do titration, we titrate to neutral. So it is actually yellow to orange. A student carried out the first titration and did not notice that there was an air bubble between the tap and the tip of the burette. Remember, when we use a burette, you shouldn't have an air bubble because that would affect your titration. The student carried out 2 accurate titrations. So his first titration was wrong. It had an air bubble. Now you should know that when we have an air bubble, that means that the volume that we have is, or the volume that we read from the burette would be too big. It would be bigger than it should be. Then he repeated it with accurate titrations when there are no air bubbles and no errors. Which of these could be the 3 titers? So we're looking for something in which the first titration is too big, and then the second and third are close to each other, smaller than the first one. So which does this apply to? It applies to C, where we have the first titer is 22.8, then he got 22.35 and 22.4, so these are correct. Then he says 25 centimeter cubed of 0.1 mole per decimeter cubed of sodium hydroxide required a titer of 18.7 centimeter cubed. What is the concentration of sulfuric acid? You should know how to calculate this. He gives me information about sodium hydroxide. So I get the number of moles of sodium hydroxide. I have concentration times volume. Do not forget to divide the volume by 1,000 to make it into decimeter cubed. So this gives me the number of moles of sodium hydroxide is this value. Then I look at the equation. He's asking me about what? About the acid. From the equation, what is the relationship between number of moles of sodium hydroxide and number of moles of sulfuric acid? You can see that the coefficient in front of sodium hydroxide is 2, in front of sulfuric acid it's 1, and that means 2 moles of sodium hydroxide we react with 1. So this number of mole we react with how much? So obviously the number of moles of sulfuric acid is half of what we have for sodium hydroxide. Now I can get what he's asking for. What is he asking for? Concentration. Concentration of the acid is number of moles over volume. The volume, again, he says it's 18.7. Please divide by 1,000 before you put it into the equation. This gives me this concentration in B. The next question says hydrogen peroxide decomposes as shown. A catalyst increases the rate of decomposition by doing what? We said one of the methods of increasing rate is adding a catalyst. Now, what does the catalyst do to increase the rate? You should remember whether we're talking about exothermic or endothermic reactions, activation energy is the difference in energy between reactants in the top. So without a catalyst, you have higher activation energy. And what does the catalyst do? It decreases the activation energy, so it makes the reaction easier to proceed. A bottle of hydrogen peroxide is labeled as 10 volume. This means that 1 centimeter cubed of hydrogen peroxide solution decomposes to produce 10 centimeter cubed oxygen at room temperature and pressure. What is the concentration of 10 volume hydrogen peroxide? Okay, so he's saying 1 centimeter cubed of hydrogen peroxide decomposes to produce 10 centimeter cubed oxygen at room temperature. Now, if we have oxygen, what is he telling me? He's telling me I have 10 centimeter cubed of oxygen, so I can get the number of moles. This is a gas. So if you use it in decimeter cubed, you use volume over 24. If you're going to put it as 10 centimeter cubed, then you're going to divide by 24,000. So in any case, we get the number of moles of oxygen. And then he says, from the equation, the number of moles of H2O2 is twice the number of moles of oxygen. When you look at the equation, 2H2O2 gives 1 O2, and that means the number of moles of oxygen, you multiply by 2 to get the number of moles of hydrogen peroxide. And then he says this number of moles, these are in 1 centimeter cubed or 0.001 decimeter cubed. So concentration is the number of moles over volume, and this is the concentration that you get. Okay. A mixture of hydrogen and iodine is left in a sealed container at 300 degrees Celsius until equilibrium is established. Now, equilibrium mixture is then cooled. The color darkens. Now, he's saying he cooled it, so he lowered the temperature. When he lowered the temperature, what happened? The mixture darkens. That means it went forward or it went backward. Remember that the one that is dark in color in all of this is iodine. So if the mixture darkens, that means that when we lowered the temperature, the equilibrium shifted to the left. Remember that the equilibrium will go to the side that is exothermic. If I cool it, it goes exothermic. And that means the backward reaction is exothermic, and that means the forward was endothermic. Remember, lowering the temperature, the reaction goes exo. If it went backward, that means backward is exo, and that means forward is endothermic. He's looking for forward. The structure of ethylamine is shown. What type of reagent will attack the slightly positive carbon? Remember, the slightly positive carbon would be attacked by something that has an extra lone pair of electrons. This is called a nucleophile. Okay, then he says, which of these alcohols will produce a carboxylic acid? So we're looking for which of these gives an acid when heated under reflux with acidified potassium dichromate. Well, let us look at this. An acid is formed if I have a primary alcohol. So P and Q are primary alcohols, so they would give an acid. But R is secondary, so a secondary will not give an acid, it gives a ketone. And S is actually a tertiary, which is not even oxidized at all. So my answer is P and Q. Two reactions of cyclohexanol are shown. What is the reagent for reaction 1? Okay, let's look at reaction 1 and be careful with the direction of the arrow. What we have is an alcohol is changing into an alkene, and that means this is removal of water to give an alkene. If I want to change alcohol to alkene, I need a concentrated acid. The reagent for reaction 2 is acidified potassium dichromate. Which equation best represents this reaction? So this is a reaction of oxidation of alcohol to ketone. How do we represent that in an equation? Remember, when we represent oxidation reactions, we write oxidation like this with O between brackets, and this gives the ketone plus water. Okay? Cyclohexanol and cyclohexene each has a peak in their infrared spectrum which is not present for the other compound. Which of these peaks? So let's take a look at cyclohexanol. This is an alcohol. So it will have the peak for alcohol which is at about 3750 to 3200. So actually my answer is C. Now cyclohexene, you should remember that alkenes, this is an alkene, will have a C double bond C stretch at about 1669 to 1645. So these are the IR spectra. Calcium carbonate decomposes on heating. Explain why calcium carbonate decomposes at a higher temperature than magnesium carbonate in terms of charge and size of the cations. Okay, so if we're talking about magnesium carbonate compared to calcium carbonate, why is magnesium carbonate decomposing at lower temperatures or calcium at higher temperatures? If you look at the carbonate, remember that the carbonate can be polarized. So comparing the magnesium ion to the calcium ion, the magnesium ion is smaller radius, and that means higher charge density. So the magnesium ion will attract the negative charge around the carbonate ion, distort the electron cloud. The polarization of the CO bond in the carbonate increases with respect to the magnesium. So this makes it easier to break up, or you could say the opposite for calcium. So calcium has larger radius, and that means lower charge density, so it will be less likely to polarize the CO bond in the carbonate ion. Calcium carbonate reacts with dilute hydrochloric acid. A student determines the initial rate of this reaction by collecting the carbon dioxide in a gas syringe and measuring the volume at regular time intervals. The gas syringe can measure a maximum of 100 centimeter cube. Calculate the maximum volume of 0.5 mole per decimeter cubed hydrochloric acid that can be added to excess calcium carbonate without exceeding the measurable volume of the gas syringe. Okay, so what we have is we have 0.5 mole per decimeter cubed of HCl, and he wants to know how much volume will give you a maximum of 100 centimeter cubed of gas. So if the volume of carbon dioxide gas is 100 centimeter cubed, you get the number of moles, divide the 100 by 1,000, of course. Number of moles is volume over 24, or you could say 100 as it is over 24,000. This gives you the number of moles of CO2. Then I look at the equation. He's comparing it to hydrochloric acid, and you can see from the equation that 2 moles of hydrochloric acid give 1 mole of CO2, and that means number of moles of hydrochloric acid should be twice that of CO2. Now I have number of moles of HCl. He's asking for volume. Volume is number of moles over concentration. This gives me a volume in decimeter cubed. I need it in centimeter cubed. That is 16.7 centimeter cubed. The results of the student's experiment are shown on the graph. So he gives me a graph of volume of CO2 versus time. And he says calculate the initial rate of this reaction. How do we calculate the initial rate? We draw a tangent at 0 and extend it to the top and find what is the volume and what is the time. Remember that rate is the volume over the time. Rate is volume over time. So 100, for example, over 360, this gives me a rate in centimeter cubed per second. The student repeats the experiment, but uses hydrochloric acid with a different concentration. He uses concentration of 0.25. What was he using at the beginning? He was using 0.5. And that means that now I am using half the concentration. State what would happen to the initial rate and the final volume. Of course, if I'm using half the concentration, then the rate will be half. And when the rate decreases by half, what is the volume of carbon dioxide collected? It will also be half of what I collected at the beginning. So 90, half of it is 45 centimeter cubed. This question is about the halogens and some of their compounds. Descending the group from fluorine to iodine, the electronegativity decreases. Explain the trend in electronegativity. So let us take a look at going down group 7 from fluorine to iodine. Why is it that the electronegativity decreases even though their nuclear charge increases? The electronegativity decreases because it has to do with the size of the atom. Now, going down the group, the atomic radius increases. That is because we are increasing the number of shells. So there will be less attraction between the positive nucleus and the bonding pair of electrons, so it will be less electronegative. Remember, electronegativity is the attraction of the electrons to the positive nucleus. So the one that is more electronegative is more likely to attract electrons to itself. If it is a bigger atom, then there will be less attraction between the nucleus and the bonding electrons. Iodate ions react with iodide ions in this equation. Explain in terms of oxidation numbers of iodine why this is not a disproportionation reaction. Okay, so let us take a look at the oxidation numbers. Do you remember how to calculate oxidation number? In IO3 minus, remember each oxygen is -2. That means I have a total of -6. Now, iodine has to be +5 in order to end up with -1. In I minus, the oxidation number is the charge, -1. In I2, there is no charge, so the oxidation number is 0. Now, what is happening? I'm starting with two different species. One of them was reduced, the other oxidized to give one species. This is actually the opposite of disproportionation. Do you remember definition of disproportionation? In disproportionation, I'm supposed to start with one species, that is once oxidized to give something and once reduced to give a different species. So this is actually not a disproportionation reaction. Now the reverse reaction would be disproportionation, but this as it is not. Okay, hydrogen bromide and hydrogen iodide reduce sulfuric acid. Identify by name or formula the compound produced containing sulfur with its lowest oxidation number. Okay, when HBr reacts with sulfuric acid, what do we get? Remember we said bromides react with sulfuric acid to give HBr, and then the HBr again reduces the sulfuric acid to give what? It gives sulfur dioxide and bromine and water. But what is he asking about? He's asking for the compound with the lowest oxidation number of sulfur. So I want a compound that has sulfur. So obviously the one formed here is the sulfur dioxide. Okay, but if I have HI, we said HI can reduce sulfuric acid to give sulfur dioxide and iodine and H2S. It can also give H2S. So which one is a compound with the lowest oxidation number? So compounds, first of all, I'm not going to mention iodine. So it's either SO2 and H2S. You can see that in SO2, the oxidation number is +4. What about in H2S? The H2S is -2. In H2S, the sulfur is -2, and he wants the one with the lowest oxidation number, so it is hydrogen sulfide. Then he says the graph shows the boiling temperatures of hydrogen halides. Explain the trend in the boiling temperatures of the hydrogen halides. So we have HF, HCl, HBr, HI. Obviously, HF is the highest, and you should realize that HF is the one that makes hydrogen bonding between the molecules. So HF forms hydrogen bonds, and this is much stronger than the other interactions. So the weaker permanent dipole-dipole interactions and van der Waals forces, these are weaker than hydrogen bond. So the one that forms hydrogen bond is the one that has the higher boiling point than the other hydrogen halides. Now, from HCl to HBr to HI, they are increasing. Why are they increasing? They have permanent dipole-dipole interactions, and they have van der Waals forces, and that increases as we go from HCl to HBr to HI due to increase in the number of electrons in the molecule's electron cloud. A sample of seawater was evaporated to dryness. The solid residue was weighed, then dissolved completely in deionized water. Excess aqueous silver nitrate was added. All the chloride ions formed a precipitate. The precipitate was filtered, washed, dried, and weighed. So he has the original mass of the solid and the mass of the silver chloride precipitate. And he's saying calculate the percentage by mass of chloride ions in the solid residue. Okay, how do we do that? What do we have? We have mass of silver chloride, so I can get the number of moles of silver chloride. Number of moles of silver chloride would be mass over molecular mass. This gives me the number of moles. And from the equation, you realize that the number of moles of silver chloride is the same as number of moles of chloride. So the number of moles of chloride is the same. Now, what is he asking about? He's asking about mass. So how do we get mass? Mass is number of moles times mR, and then the percentage is that mass over the original mass of the solid residue times 100. This gives you the percentage. This question is about some halogenoalkanes. Give the classification of each halogenoalkane as primary, secondary, or tertiary. Okay, this first one is what? Obviously, you should realize if the carbon is attached to two other carbons, this is a secondary. So you can write it like this, or you can write it out in words. This is a secondary halogenoalkane. What about this one? This one, the carbon that has the Br is attached to only one carbon. So this is a primary halogenoalkane. Samples of 1-iodobutane and 2-chloro-2-methyl-propane were hydrolyzed using aqueous silver nitrate in ethanol. Explain whether or not it is possible to predict the rate of hydrolysis of these two compounds. Okay, let's take a look at the compounds. 1-iodobutane. This is 1-iodobutane. 2-chloro-2-methyl-propane. So that's this. Okay, which one should react faster? Well, let's see. One of them is a primary halogenoalkane, so 1-iodobutane is primary. The other one, 2-chloro-2-methyl, this is a tertiary. So a tertiary should react faster. But then we have different halogens. We have a Ci bond in the 1-iodobutane, and we have a CCl bond in the 2-chloro. Which one should react faster? You should remember that the Ci bond breaks up more easily than the CCl. So actually the iodo should react faster. So taking these two into consideration, it is not possible to predict which compound will react faster, because the 2-chloro-2-methylpropane should react faster since it's tertiary. But the 1-iodobutane should react faster because the Ci bond is weaker, easier to break than the CCl bond. So overall, it is not possible to predict the relative rate of hydrolysis of these two compounds. Butylamine is formed when 1-bromobutane reacts with excess concentrated alcoholic ammonia. Give a reason why this reaction should be carried out by heating the reactants in a sealed tube rather than heating under reflux. So he's saying I shouldn't heat it under reflux. You remember what is heating under reflux is when I put the condenser like this and I heat it, and whatever evaporates should cool and come down, but then ammonia would be lost if I heat it like this. So we do not heat it under reflux to prevent ammonia gas from escaping from the condenser. Then he says complete the mechanism for this reaction by adding curly arrows and any relevant lone pairs and dipoles. So the ammonia is attacking at the Br bond. You realize that this is a nucleophilic substitution, so the lone pair of electrons from the nitrogen will attack the slightly positive carbon because the Br would be slightly negative, so the electrons go to the Br, and then we have another ammonia molecule from its lone pair of electrons will attack the hydrogen to remove it, and the electrons go to the nitrogen, and this gives me my final product. Okay? Bromoethane is prepared by reacting ethanol with potassium bromide and concentrated sulfuric acid. Calculate the maximum mass of bromoethane that could be prepared from this mass of ethanol and this mass of potassium bromide and this mass of sulfuric acid. So first of all, he's giving me information about all three reactants. Remember that when we have information about all reactants, we're supposed to get the number of moles of each one and then compare to determine which one is a limiting reagent. So we need to get the number of moles of each of these. So I have the molecular mass of ethanol, the number of moles would be that mass over the molecular mass. The molecular mass of KBr, number of moles of KBr will be the mass over that molecular mass. The number of moles of sulfuric acid is also the mass over the molecular mass. Now, compare all the number of moles. Number of moles of ethanol is 0.10109. Number of moles of KBr is 0.125 something. Number of moles of sulfuric is 0.166 something. So the limiting reagent, if you look at the equation says they should all be the same. So the limiting reagent is the one that has the lower number of moles. So which one has lower number of moles? The ethanol is obviously the limiting reagent. So that means if I have 0.101 of ethanol, I should need only the same number for KBr and the same number for sulfuric. So the other are excess. So we decide that ethanol is the limiting reagent. So it is this number of moles of ethanol that we're going to compare to the bromoethane. Look at the equation. The bromoethane should have the same number of moles. So the number of moles of bromoethane is the same as that of the ethanol, and that means that I can get mass. Mass is number of moles times the MR of the bromoethane. That means I need to get 11.01 grams. The reaction between 2-bromopropane and potassium hydroxide takes place under two different conditions. So he's reacting 2-bromopropane with potassium hydroxide, once in aqueous solution and once in ethanolic solution. Do you remember these two equations? If I have a bromoalkane and I react it with potassium hydroxide, okay, if I react it in aqueous, you should remember aqueous means the Br is replaced by OH, so it gives me the alcohol. But if I'm doing it in ethanolic or alcoholic solution, Then this is now a elimination reaction. So I remove the H and the Br and I form an alkene. So he's saying compare and contrast between these two reactions. Well, both reactions will require heat under reflux. But what is the difference between them? In aqueous, this is a nucleophilic substitution reaction, and the OH minus is acting as a nucleophile and it forms an alcohol, while in a ethanolic solution or alcoholic solution, the reaction is elimination reaction, and the OH minus in this case is taking that hydrogen, that bottom hydrogen, so it's acting as a base and it forms an alkene. He doesn't want mechanism, but he does want the equations for the reaction. Fuels burn in oxygen to release a lot of energy. Many hydrocarbons and alcohols are used as fuels during complete combustion. They produce carbon dioxide and water. And he's talking about 2,2,4-trimethyl pentane, promotes smooth combustion in petrol. Alcohols such as methanol and ethanol can be used as fuels either on their own or as additives. So the first question says, he gives me the standard enthalpy change of combustion, and he's saying first state the two standard conditions for this enthalpy change. When we say this is standard enthalpy change of combustion, what are the standard conditions? You should remember that standard conditions are pressure is 100 kilopascal or 1 atmosphere, and the temperature is 298 Kelvin or 25 degrees Celsius. Write the equation for complete combustion using molecular formula. Okay, this is 2,2,4-trimethylpentane. So if I want to write the molecular formula, this is C8H18. Now, combustion means I'm reacting it with oxygen. Complete combustion means it gives carbon dioxide plus water, and then you need to balance. Okay? Draw a labeled enthalpy level diagram for complete combustion of an alkane. Remember, complete combustion means it is exothermic or endothermic. Complete combustion of an alkane is exothermic. So how do we draw the energy level diagram for an exothermic reaction? The standard, he already tells me that the standard enthalpy change of combustion is minus 5461. So minus means it is exo, and this is how we draw the enthalpy level diagram or the energy level diagram. The reactants will be on top, the products below, and an arrow going down because the delta H is negative. Okay, calculate the heat energy release during the complete combustion of 1 decimeter cubed of this alkane. Okay, so I have 1 decimeter cubed of this alkane, and he's telling me that the delta H of combustion is minus 5461 kilojoule per mole. So I want to determine the number of moles first. Now, how do I determine the number of moles? He's giving me a volume of a solution. Now, density is this. Actually, it's a volume of a liquid. Density, he gives me, you know that density is mass over volume, so I can use that to get the mass. Mass is the density times the volume, which is 1 decimeter cubed. Remember that he gives me the density in gram per centimeter cubed. So in this case, I have to change the 1 decimeter cubed to centimeter cubed. So this gives me 692 grams. So that is my mass. I want to get number of moles. Number of moles is mass over molecular mass. This gives me the number of moles. Now he's telling me that I have a delta H minus 5461 kilojoule per mole. So I need to multiply that by the number of moles to get the total delta H. So this will give this number in kilojoules. In an experiment to determine the enthalpy change of combustion of ethanol, a student uses the apparatus shown. He has the mass of water is 100, mass of ethanol is 0.305, temperature rise is 13.2. Calculate the enthalpy change of combustion of ethanol. Okay, in order to get the delta H, I need to calculate Q, and you should realize that Q is mc delta T. And remember, M stands for what? M stands for the mass of water. It does not have to do with the mass of ethanol. This is mass of water, so M is 100, C is given, the temperature rise is given, so this gives me a certain energy in joules. So this is the total amount of energy. Now we need to get number of moles. The MR of ethanol is 46, so the number of moles is the mass over the molecular mass. Now we know that delta H is what? Delta H is Q over N. So the Q that we calculated in kilojoules, remember it came out on the top in joules. Now, if I want to put it in delta H, it is preferable to put it in kilojoules. So you're dividing by 1,000. So this is now 5.5176 divided by the number of moles. This gives you a certain number. Remember that this is combustion of an alcohol. Combustion of an alcohol is exothermic. So you have to put a minus sign. So this is a negative number. So my delta H is minus 832. The uncertainty in each thermometer reading is plus or minus 0.05. Calculate the percentage uncertainty in the temperature rise in this experiment. Okay, remember that for any thermometer, what you're doing is you're reading an initial temperature and you're reading a final temperature. So you're actually having this uncertainty twice in each reading. To get the percentage uncertainty, it is 2 times the 0.05 over the reading we're talking about times 100, because this is a temperature difference. 13.2 is the temperature rise. So this gives me an uncertainty, percentage uncertainty of 0.76%. The student looked in a data book and found the actual value for the standard enthalpy change was more exothermic. So the value is actually larger than what we got. Give 2 reasons for the difference between data book and experimental value. Remember, when we do this kind of reaction, the value that we get for delta H is always less than the value in the data booklet. Why? Because we either had loss of heat to the surroundings, or we had incomplete combustion of ethanol, or because some of the ethanol evaporates, so actually the number of moles that we calculated is not the correct number. Enthalpy changes for conversion of 4 compounds in the gas state into their constituent atoms are shown. Calculate the bond enthalpy of the C-C bond in kilojoule per mole. Okay, the C-C bond we can get from all of these bonds. So that first equation is giving me the delta H for breaking of the bonds in water. Well, when we break the bonds in water, we're breaking 2 OH bonds. So each OH bond, you divide that delta H by 2 to get the bond enthalpy of each OH bond. Then the second equation is giving me the delta H when I break the bonds in methane. Well, here I'm breaking 4 CH bonds, and that means each one will be that number divided by 4. Then the third equation is giving me the delta H for breaking up of methanol. Well, that means that I'm breaking 1 CO bond, 3 CH bonds, 1 OH bond. That is the delta H that I have. So from all of that, I can get the CO. The CO will be the delta H that we have minus, we already got the bond enthalpy for each CH bond. We have 3 of them. And we already got the bond enthalpy for the OH bond. That gives me the bond enthalpy for the CO bond. Now, if I look at ethanol, can I see the bonds that are being broken? Well, I have one CC bond, I have 5 CH bonds, one CO bond, one OH, and that is the total delta H that he gives me. From that, I can get the CC bond. So it is that value minus the total of all the others. So this gives me a certain number for the bond enthalpy for the carbon-carbon bond. Last question says ethanol can be manufactured by reacting ethene with steam. This reaction is usually carried out in industry at 300 degrees Celsius and 70 atm. Explain the effect on the equilibrium position and the yield of ethanol if the reaction is carried out at what? The same temperature, but we're increasing the pressure. Instead of 70, I'm going to put 200 atm. Now, he tells me that this reaction is exo. The forward reaction is exo. Delta H is minus 45. So the forward reaction is exothermic. Now, if we're talking about temperature, we look at which side is exo and which side is endo. And remember that increasing temperature will cause it to go to the side that is endo. But here, what are we doing? We're increasing pressure. Now, when we increase pressure, it goes to the side with what? It goes to the side with less number of moles. So in this case, when I increase the pressure, it will go forward to give less number of moles. And that means it will give me more ethanol. So the yield of ethanol would increase. Do we understand this? Okay. I hope that was useful to you. Thank you for listening.